All right, another part of radiation is predicting how long it's going to take for the radiation to go away. To do this, we use what's called half-lives of the radiation. And what scientists did is they would get a sample of an element, and they would say, all right, we're going to start out with right on this line. Sorry, it's not like right on there. I'm not like perfect at this. We're going to say that that is 100 grams. And then we're going to measure the time that it takes to go from 100 grams till there's only half of that left, and that is where it's going to be 50 grams. Okay, and then we're going to measure the time for that to go halfway. And that's going to be 25 grams. And then the time for that to go halfway. And that's going to be 12 grams, 12.5 grams. And the time for half of that to go away. And that's going to be 6.25 grams, and so on and so forth. When they did this, they found that there was always a pattern that emerged. We'd start there with 100 grams, and then there would be 50, and then there would be 25, and then there would be 12.5, and then there, and then there. And we had this exponential decay that always took place. Okay, so scientists said, well, okay, if this is always going to happen, then if I have 0.8 grams of carbon-14, how long ago would I have had 28 grams of carbon-14? Okay. They did the calculations and everything. They found out that the half-life of carbon-14 was 5,270 years. No, sorry, 5,720 years. Okay. So we're going to go 0.8, and we're going to times this by 2 because we're starting with 0.8 and we want to go back. If we were going forward, then we divide by 2. Then so here we're going to get 1.6. Keep going until we get to the 28 we want. 3.2. All right, so here between this step and this step is where we get to the 28 we want. In our class, we're not going to do any halves or any fractions or anything like that. So we're just going to say, okay, I was here, I wasn't to it yet. Here I went past it, so we're just going to say call this good. We're not going to do any division. So we go through, we say I times it 1, 2, 3, 4, 5, 6 times. So 6 half-lives had to have gone by to go from 28 grams of carbon all the way down to 0.8 grams of carbon. Well, if each half-life is 5,720 years, 6 of them have gone by. Then 34,320 years had to have gone by. And this is how we do carbon dating today. in every sample of carbon that we have, so we have a bone, and see if this looks anything like a bone. I know I'm not the best artist in the world. It is going to be made up of carbon 12, carbon 13, and carbon 14. Okay, as long as we're living, we're constantly replenishing these three things. Carbon 14 happens to be radioactive. It will go away. These two will last essentially forever, and they never go away. And there is a certain ratio of these elements to each other. When we find a bone in the ground, then we can say, okay, here's my carbon ratio, my carbon 12 ratio, my carbon 13 ratio. This is how much carbon 14 has gone. So we can say this is how much time has passed using this analogy. And we can accurately date how long ago something lived. We can also use this with uranium-236 to judge how old the world is, since it was first formed. So this is useful in many of those different types of scenarios.